When the critical coupling coefficient is very high, so it is found in graphs that you two frequencies where you get maximum power transfer. So that is what we have mathematically derived. So two frequencies are omega equal to plus or minus omega naught into this expression, and everything depends on B. B is the factor by which will determine how much your critical coefficient of coupling is more than your critical coupling coefficient Kc. So you know K is equal to B into Kc. Okay, K is equal to B into Kc, and ideally the value of B is going to be more than 1. It cannot be less than 1. B is going to be 1.1 times or 1.2 times or 1.352, like that. B is going to be some integer or it may be fractional multiples of Kc. So only when this condition B greater than 1 is going to happen, maximum power transfer takes place at single frequency, two frequencies. So in other cases, when the B value is very less, you cannot expect the power transfer takes place at two different frequencies. When you put B is equal to 1, you get one frequency where power transfer takes place, omega equal to plus or minus omega naught. So at only at one particular frequency where your power, which is going to be resonant frequency, right? So for you to have a maximum power transfer at two different frequencies, you have to ensure that the coefficient of coupling is very large when compared to your critical coefficient of coupling, and this facility is available only in double tune amplifiers. Single tune amplifiers, you know, the power transfer, maximum power transfer takes place at only one particular frequency. Only in double tune amplifier, for a particular coefficient of coupling, we can have maximum power transfer happening at two different frequencies. So that's what I said. In double tune we derive two expressions. One is we find the frequencies where maximum power transfer takes place, and another is the derivation where you actually find the bandwidth of your double tune amplifier. So the first derivation is done where we have found out the two frequencies where the power transfer is going to be maximum. Now we have to go with the bandwidth. The same steps we are going to repeat. See, only one thing. For maximum power transfer, we equate I2 equal to I2 max. For bandwidth, we have to equate I2 equal to 1 by root 2 times I2 max. Or you will, in decibel scales, we'll be subtracting. Okay, or in decibel scales, we'll be subtracting. So, but since all our derivations are based on numerical parameters, we'll equate the actual current value to 1 by root 2 times the maximum current value. So I2 is equal to 1 by root 2 times I2 max. I2 expression we know, I2 max expression we know. We are going to do the same thing, same approximation. We are going to do L1 equal to L2 equal to L, C2 dash equal to C, R0 dash equal to RA dash equal to R, and the reactant term I'm going to have it as JX. So when I substitute everything in the above equation, it becomes very simple. It becomes very simple. And now I'm going to again solve this equation, cross multiply, I'll get this. Now I'm again going to solve this equation by removing the